Telescope ever launched into space made another successful step on its journey to a point 1 million miles away from Earth today.
For years, astronomers have peered into the depths of the cosmos with hope, imagination, and patient anticipation, waiting for the moment when the James Webb Space Telescope JWS would reveal something so baffling that it would redefine our understanding of the universe. That moment has finally arrived. After years of drifting silently through the void and gazing farther than any human-made instrument has ever dared, the JWST has stumbled upon an encounter that many scientists once believed to be outright impossible. Not only does this detection challenge current astrophysical theories, but it also calls into question the very structure of time, space, and the evolution of the universe. Before we start, smash the like and subscribe buttons for more updates. At the heart of this groundbreaking discovery is a distant object, an ancient, hyperluminous galaxy cluster nestled at the edge of the observable universe. What makes this cluster so astonishing isn't merely its size or brightness, but rather its age. Based on its redshift and spectral characteristics, the JWST measured this structure to have formed just a few 100 million years after the Big Bang. According to the standard model of cosmology, this level of complexity, organization, and mass should have been physically impossible to achieve in that amount of cosmic time. The light reaching JWS today from this cluster has traveled over 13.4 billion years, and yet, the system it originated from appears as evolved and mature as galaxies that are billions of years older. This alone would have been enough to stir a frenzy within the scientific community, but the data only deepened the mystery. The cluster includes elliptical galaxies with dense bulges and stellar populations usually associated with far more recent epochs. In addition, gravitational lensing effects observed in the data imply the presence of enormous quantities of dark matter. Far more than theoretical simulations had ever predicted could assemble in the universe's first few 100 million years. Furthermore, embedded within the cluster was a supermassive black hole whose mass rivals those found in the centers of modern giant galaxies. Such behemoths typically take billions of years to grow, accreting material over eons. Yet here it was, thriving in a cosmic era where such structures were presumed embryonic at best. Scientists have spent decades refining the LCDM model, Lambda Cold Dark Matter model, which outlines the universe's evolution from the Big Bang through the development of stars, galaxies, and cosmic structure. This model suggests a relatively slow hierarchical process, with smaller structures forming first and merging into larger systems over time. What the JWST has encountered, however, seems to bypass that timeline entirely. The newly discovered cluster demonstrates a level of organization and mass density that appears to mock the gradual evolutionary pathway established by theoretical cosmology. It's as if some unknown mechanism jump-started galaxy formation, operating under rules that current physics has yet to uncover. The implications of this encounter are profound. First, it forces cosmologists to reconsider how quickly the universe cooled and stabilized after the Big Bang. The early universe was believed to be a seething soup of hot plasma and energetic particles, gradually forming neutral atoms during the epoch of recombination. Only after this could matter clump together to form the first stars and galaxies. Yet, if such mature structures already existed at this time, the process must have been not only rapid, but governed by an unknown accelerating factor. This discovery also casts a spotlight on dark matter and dark energy, the invisible scaffolding believed to hold the cosmos together. The excess gravitational lensing observed suggests concentrations of mass that shouldn't be possible in the early universe under existing theories. It raises questions about whether dark matter behaves differently at different epochs, or whether it may be interacting with ordinary matter in previously unknown ways. If true, this could revolutionize the hunt for dark matter particles, refocusing experimental efforts away from conventional weakly interacting massive particles, WIMPs, and toward more exotic candidates like axions, sterile neutrinos, or even entirely new classes of quantum fields. Further compounding the mystery is the presence of mature metallicity levels in the detected galaxies. Metals in astrophysical terms refer to elements heavier than helium, which are forged in the nuclear furnaces of stars and spread through supernovae. These processes take time, hundreds of millions to billions of years, to enrich the interstellar medium sufficiently. Yet spectroscopic analysis of the cluster reveals that many of its stars already contain high levels of iron, oxygen, and carbon. Such enrichment suggests that these galaxies must have undergone not one, but multiple generations of star formation in a time span shorter than any known model permits. The role of time itself now stands under scrutiny. If these structures formed earlier and evolved faster than predicted, then perhaps our assumptions about the flow of cosmic time, especially in the early universe, require adjustment. Some theoretical physicists are already drawing parallels to alternative models of cosmology, such as the ekpyrotic scenario or varying speed of light theories, which challenge the constancy of fundamental forces and constants across cosmic epochs. These were once considered fringe ideas, but with the data now in hand, they may deserve a closer look. And then there is the black hole, the monster lurking at the center of one of the galaxies, devouring mass at a rate that defies reason. How it could have reached such a size in such a short period of time is not just a problem, it's a crisis for black hole growth models. The traditional path involves the collapse of a massive star into a stellar mass black hole, which then grows slowly through accretion and mergers. However, this object's mass suggests either a radically new mechanism of black hole formation or a fundamental gap in our understanding of how matter behaves under extreme conditions. Some researchers are now contemplating whether this may be evidence for direct collapse black holes, hypothetical entities formed when colossal gas clouds collapse under gravity without fragmenting into stars. This idea has been around for a while but lacked observational support. The JWST's detection could be the first real confirmation that such a mechanism is not only possible, but perhaps common in the infant universe. Alternatively, this could imply the existence of primordial black holes, objects formed not from collapsing stars, but from quantum fluctuations in the moments just after the Big Bang. If proven, this would offer an entirely new perspective on the distribution of matter in the early cosmos, and potentially even on the origin of dark matter itself. Another perplexing aspect of the encounter is the geometry of space around the cluster. The gravitational lensing distortions observed are unusually complex, suggesting warps in space-time more intense than expected for such distances. This may point to local curvature effects not accounted for in general relativity, or hint at interactions with structures outside the observable universe. The possibility that these observations are touching the edge of a multiversal boundary, regions where different physical constants apply, is, while highly speculative, no longer entirely off the table. Equally captivating is the possibility that what JWST has found may not be a galaxy cluster at all, at least not in the traditional sense. Some fringe theorists are beginning to propose that it might be a relic from a previous cosmic cycle, an echo or residue of a pre-Big Bang universe embedded in our own. This view aligns with certain models of cyclic cosmology, where the universe undergoes endless periods of expansion and contraction. If this were true, then the JWST may have captured light not just from the farthest reaches of space, but from a previous epoch of existence altogether. What makes the situation even more enthralling is the precision and clarity with which JWST has delivered these findings. Its gold-coated mirrors and infrared sensors were built precisely to reveal such deep-time wonders, and it has not disappointed. The detail captured in the structure of the galaxies, the distribution of star populations, and the interplay of gravitational forces paints a picture both beautiful and unsettling. It is a portrait of a universe that formed far faster, far more violently, and far more mysteriously than anyone had previously dared imagine. Some physicists are now re-examining the inflationary model of the early universe. Inflation posits a sudden exponential expansion of space in the moments following the Big Bang. This expansion helped to smooth out irregularities and laid the groundwork for cosmic structure. But if structures like this ancient cluster existed so early, it suggests that inflation may have left behind more than just quantum ripples. It may have directly seeded dense regions capable of forming supermassive galaxies almost instantly. Alternatively, inflation itself might need to be modified to include high-density anomalies as part of its mechanism, a direction that could radically alter our understanding of the universe's birth. There's also the potential role of quantum gravity to consider. Quantum effects are typically negligible on large scales, But in the moments after the Big Bang, and perhaps even now in extreme conditions, quantum gravitational phenomena might play a role in shaping the cosmos. Some theories, like loop quantum gravity or string theory, have suggested that the early universe could behave in non-intuitive ways, creating bubbles or pockets of accelerated evolution. If what JWST has seen is a result of such phenomena, then it represents the first observable link between the macroscopic structure of the universe and the quantum realm. The discovery also reignites debate over the concept of cosmic variance and the anthropic principle. Could it be that our universe or our region of it is an outlier in terms of structure formation? If so, this encounter may not be representative of cosmic norms, but rather a statistical anomaly, an extremely rare fluctuation that just happens to fall within our observational reach. Alternatively, this might reflect a deeper truth, that the laws of physics we know are only local expressions of a broader, more complex multiverse. If the constants of nature, like the gravitational constant or the fine structure constant, are variable across spacetime, then what JWST has found might simply be evidence of another cosmic neighborhood with different rules. The reaction within the scientific community is one of measured awe. No one is ready to throw out decades of theory overnight, but there's a growing consensus that something fundamental has been missed. Whether it's a missing piece of the cosmic puzzle, an entirely new paradigm, or a deeper layer of hidden reality, the James Webb Space Telescope has now pushed humanity into a new era of cosmic exploration. We are no longer merely observing the universe, we are confronting its contradictions, peering into its paradoxes, and brushing against the edge of the unknown. If you liked this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us, what are your thoughts on what James Webb just discovered deep in space? We want to hear from you. Thank you for watching and see you next time.